Testing. Can you hear me? But the mic is not on. Testing. Okay. Let's try again. So, good evening, everybody. It's nice to see you. I was telling Amari that this room brings back memories. I was here in my first year doing math 111 and chemistry 111, and some of you guys as well. So it's a nice feeling. And I'm very happy to welcome Professor Peter Dunsby. We go also some ways back. If I may say, he was my master's, one of my examiners for M, and luckily he passed me. So thank you, Peter, for that. We are very happy that you are here and visiting us, and also you work with Amari. You were his supervisor, right? For PhD, masters, okay.
And PhD.
And PhD, both of them. Okay, but I think you did a good job. So welcome. So I'm just going to physics. He also works closely with his graduate students and postdocs. He's regularly invited to lecture at local and international meetings, and he has a proven track record of fundraising and management of large grants. So this is an interesting one. In 2003, he secured the bid to host NASP. Now we know about NASP, the National Astrophysics and Space Science Program. It started way back in Cape Town and later on moved into the rest of the country, and we also host a node here at Northwest. But he secured the bid to host it at Cape Town at the time, and he was director of the program until July of 2013, so a decade, eh? 2013, so a decade, eh? Over the past 19 years, NASP has made a major contribution to human resource development in astronomy and space science in South Africa. In 2006, he was awarded the British Association Silver Medal from South African Association for the Advancement of Science. And in 2016, the National Science and Technology Forum, or NSTF Award, for Human Capacity Development. In 2017, he was elected to the College of Fellows of the University of Cape Town. Now, I told him I was looking forward to some of his beautiful photos because he's an obsessive astrophotographer. And he's going to show us some of his beautiful work. And he also runs his own home observatory, and he's very active in school outreach. So we're looking forward, and he's going to speak to us about his hobby and his job. And we're looking forward to hear about dark energy, maybe dark matter, and also astrophotography. So welcome again, Peter. It's really nice to have you.
Thank you very much, Chris. Thanks very much, Christo. It's very nice to be here. Do we need to dim the lights a bit, or so we can see the screen? Yeah, that's better. Great. So this talk is going to deal with two very distinctive topics, somewhat related, a little bit related, because they are both to do with space. The first part relates to essentially my day job. So I'm a cosmologist. I also lecture, and it's called a job, but I'm sure other academics in the room would agree that in some sense, if you're doing what you really enjoy doing, it's hardly a job. And sometimes I have to pinch myself and think, gee, I'm being paid to do this stuff. It's really quite amazing to be able to do a job, and it's in some sense also a hobby. And then the second part is going to deal with something which I got involved in about 4 years ago, mostly as a sort of knee-jerk reaction to having to serve as head of department, and I needed something to distract myself away from the grind of having to manage a big department. And I stumbled upon astrophotography and fell in love with the process. And this is kind of what I do in the evenings now. So I've got my day job doing cosmology, and in the evenings taking nice pictures of the night sky. So the talk's going to be about both. So my day job, as I mentioned already, has to do with teaching undergraduates and also postgraduates. But I also get to do research in cosmology, which has become, in the last couple of decades, really a sort of new frontier for the study of fundamental physics. In some sense, you can think of the universe as being one gigantic particle accelerator on the very high energy scales, and also a big sort of gravitational machine for giving you information about how the gravitational field operates on very large scales. So it's become a very powerful tool for dealing with all of these fundamental questions. And of course, it deals with some of the big questions. You know, did the universe have a beginning? Did it, is it going to have an end? What's the nature of the end of the universe? That's a big fundamental question which we hope to answer. What's the nature of matter in the universe? And this is something which most cosmologists have been working on tirelessly for several decades now, really trying to unravel the nature of matter. Because at the end of the day, what we see in the universe, when we point a telescope to the night sky, in the optical, what we see with our naked eyes, is only a tiny fraction of the total matter content in the universe. And this is what's really mysterious about modern cosmology. There's a large fraction of the matter of the universe which is virtually unknown. And it's something which we hope to understand in the coming decades. Another question, of course, relates to, do we occupy a particular special place in the universe? Is our location in the universe unique? We believe it not to be the case, but this is something which we hope to be able to test with astronomical experiments in future years. But ultimately, the aim is to provide a complete description of the universe based on mathematics and fundamental physics. So, and we're dealing with scales which range from at very early times in the early universe, less than 10 to the minus 35 meters, so right in the sort of Planck era of the universe, at the very beginning of the universe. You're dealing with very high energy and very small scales, and are of the order of 10 to the 26 meters. So a huge range of scales need to be covered and understood in some unifying description, physical description of the universe. So it's quite challenging to if you think of what you're trying to achieve, the fact that we have a basic theory that seems to work rather well, I find quite remarkable. So we have a simple model, and it does seem to explain the large-scale features that we see in the universe, and matches up very closely with our statistical measurements or observational measurements of the large-scale structure that we observe. So the starting point in all of this process is to try and build models of the universe, and then you have to test them. So how do you build a model of the universe? Well, you have to make a bunch of assumptions, because the equations that you are dealing with are generally far too complicated to solve exactly, or even numerically. So you try and make your life simpler by making some assumptions which are based on how you observe the universe. And one of the assumptions that people generally make is that the universe is highly symmetric, right? So it's homogeneous, so it's very smooth. The matter is distributed very smoothly throughout the universe. And also it's isotropic. In other words, if you look in different directions, the universe looks more or less the same in all directions. So these are the two basic assumptions that underlie the basic theory of cosmology. The other assumption, of course, relates to the kind of theory of gravitation that you want to put into this theory. And back in 300-400 years ago, this would have been the Newtonian theory of general relativity, or variants of that theory that we can use as our theory of gravity. So then, having made those assumptions, we try and solve Einstein's equations, which in general is extremely difficult, but with these assumptions can be done. And once you've got a solution, you can make predictions, and then you can compare those predictions with reality, with your observations. And that's the kind of process that we try and follow in our model building and our model testing. And we seem to have arrived with a model of reality, if you like, reality in inverted commas, which does seem to match the observations, what we see, rather closely. So this is a public talk. It's not meant to be highly technical, but I can't but show you at least one or two equations, because this essentially is our basic theory of cosmology. It can be written down on a postage stamp. And it's remarkably simple. It essentially boils down to the same mathematical analysis of throwing a ball up into the air. You know, when you throw a ball up into the air, it reaches up to some maximum height and it comes back down again. The harder you throw, the higher it gets. So you can kind of think of the distance away from your hand as being the radius of the universe. And when cosmology was being developed, some of the simplest early models of cosmology were exactly that. They started with a hot Big Bang, they expanded out to some maximum radius, and then they recollapsed to a big crunch. Then you keep throwing the ball harder and harder, and eventually you escape the Earth's gravitational pull, and the ball shoots off into space and keeps on going. But it keeps on going at a slower and slower rate. So there's another class of models, not Big Bang, Big Crunch, which start with a Big Bang. They are ever expanding, but they're expanding at a rate which is slowing down. Okay? So that's where your ball, that sort of analogy, that ball has escaped the Earth's gravitational field and is now moving away at a rate which is slowing down. But the kind of models that we're now looking at have some strange matter content in it called dark energy, which I'll say more about later, which has a sort of anti-gravity effect to it. So now you're throwing a ball up, it escapes the Earth's gravitational field, but instead of expanding at a slower and slower rate, it now starts to accelerate away from the Earth. Right? So your ball is not slowing down, it's in fact speeding up. So the expansion rate of the universe appears to be speeding up at a faster and faster rate today due to the fact that dark energy is dominating today. And in between these two kind of extremes, where you've got a decelerating universe and an accelerating universe, you have this kind of tipping point, which you see here on, at the sort of at the maximum of this curve here, which was a solution, in fact, discovered by Albert Einstein, where the universe sits there at some constant radius. It's static. It's not expanding. It's not contracting. It's just sitting there at some constant radius. It's static, but you can see from this picture that it's highly unstable. So if you were to knock the ball at the top of the hill a little bit to the left or the right, or to the right, while to the left it would roll down and go to a big crunch, and to the right it would start accelerating at a faster and faster rate. So this Einstein's static model that Einstein was very fond of and had to discard because it was shown not to be correct, is the sort of tipping point between these accelerating and accelerating models. Another way of writing the equations, and I promise this will be the last equation, the last set of equations, is in a way where you kind of write things in terms of quantities which can be observed. So here we have basically the amount of matter and dark matter, plus the amount of dark energy, or cosmological constant, plus a term here which measures the shape of the universe. And all of these things have to add up to 1, right? So this is your theory. All of these numbers have to add up to 1. And the task of the observational cosmologist is to go out and to try and measure these quantities and check that you indeed get everything to add up to 1. So that's kind of what people have been doing simplistically for the last 30 or 40 odd years, is measuring the different contributions and determining to see whether they normalize to 1. There's another parameter, Q, here, which measures the rate at which the universe is expanding. It's called the deceleration parameter. It was defined this way because back in the day, we never expected to discover that the universe would be accelerating. So it was defined in such a way that it would always be positive. But now we've discovered that, in fact, in the present epoch, the value of Q is in fact negative, indicating that the universe is accelerating. And you can see that it's given by this sort of fight between two terms, one dark matter, dominated by dark matter, and one dominated by dark energy. And if dark energy is bigger than dark matter, then the universe accelerates. So the game, in a very simplistic way of cosmology, is to try and make everything add up to 1, right? So that's what we've been trying to do all this time. So there are a bunch of observations that can be made to try and determine these different terms. The first 2 here relate to determining the sort of visible matter content and the dark matter content. And this can be done by looking at rotation curves of galaxies, so the speed at which stars move around galaxies. So that's kind of a local effect of dark matter. And you'd expect that as you go further away from the galactic center, the speed of your star would fall off. But in fact, what tends to happen is it sort of reaches some plateau. It never kind of falls off. And that indicates that there's some hidden dark matter which is preventing the fall off of the velocity of the orbiting stars. So that was done many years ago, and that was the first bit of evidence pointing towards dark matter. And then more recently, you can do this on a cosmological scale by measuring the amount of dark matter by looking at lensing or the bending of light around clusters of galaxies and large-scale structures. So you can infer what the missing matter is by determining how the light bends around these gravitational objects, which are typically clusters of galaxies. So when you do this, this typically gives you a contribution to standard matter or dark matter of about 30%, roughly. It's a little bit less than that, but 30% is a good number to use. Then you can do something else. You can try and measure what the curvature or the geometry of the universe is, and this can be done by looking at light, which is propagated all the way back from around 300,000 years after the Big Bang to the present day. And depending on the shape of the universe, the light will behave differently. So if the universe is geometrically flat or Euclidean, typically photons will move in straight lines and they'll remain parallel. But if the universe is spatially curved, either open or closed, then that will lead to the photons moving apart or towards each other. So you can determine by mapping on the sky these photons, these microwave background photons, exactly what the geometry of the universe is. And it was discovered that this parameter omega k is very close to 0. It slightly favors a closed universe, but only very, very slightly. Essentially, the universe is geometrically Euclidean. It's almost flat. So that leaves you with a problem, you see. You basically end up with 30% coming from dark matter, and nothing coming or virtually nothing coming from the spatial curvature. And that means that there is something over here, okay, that we don't know anything about, which, in order to make things add up to 1, has to contribute about 70% of the matter content of the universe. And this is the dark energy problem. What is dark energy? Why is the contribution to the matter of the universe so much dominated by dark energy today? And this is something which I'm sure is going to occupy our minds for a long time to come, really trying to determine what this something else is that we need in order to make our model work. So just to summarize this sort of current situation, we have basically this guy here dominating today. It's negative, so that means Q is negative because it's dominating the matter content, the standard matter content, and that means that the deceleration parameter is negative, and therefore the universe is accelerating today. And the universe appears to be Euclidean. It's essentially flat. So that's kind of the current status, and the job really now is to try and understand why it is that this way, and what dark energy actually is. So again, sort of visualizing the sort of different contributions on a pie chart, just to sort of emphasize just how extreme the problem is. So if you look at the different contributions, visible matter it only really accounts for about 5%. And the rest is kind of, and that's known, that's kind of the kind of stuff that we deal with in our labs at university. We can pick a phone up. This is standard matter, right? So this is known. And 95% appears to be unknown. So this is the dark matter and the dark energy. I think we have a better chance of really getting to grips with dark matter, but dark energy is completely mysterious. We have absolutely no idea what dark energy is. Okay, so the question is really, well, how do we know that dark energy exists? You know, so it could be that it relates to the simplifications that we've made in our model building, right? So we've made a lot of assumptions to get to this stage. We've built a model where we've essentially assumed a theory of gravity to be Einstein's theory of gravity. We've assumed the universe to be modeled by the so-called Friedman metric, which is homogeneous and isotropic. We've made some assumptions about the initial conditions in the early universe, et cetera, et cetera. So it's a little bit like, you know, if you go far enough away from a cow, if you're looking at a cow in the distance, well, you can approximate it very well with a sphere, right? Cows are, roughly speaking, spherical. But, of course, we know cows are not spherical, right? So this is an example of what we refer to as the fitting problem. In this case, we fit a sphere to a cow. It kind of works, but in reality, it's not a sphere. So it could be that dark energy doesn't exist, and it's just related to the fact that we're trying to fit the wrong model to the data, and therefore the acceleration of the universe is an artifact of that. It's a mirage. So we've taken some crude model, the model that we like, nice and simple. We fit it to the data. That infers values for the parameters. That tells us then that the universe is accelerating. And we're kind of now stuck because we're trying to understand why the universe is accelerating, what is causing the universe to accelerate. So it could be that dark energy doesn't exist, and it's just a failure of the fitting of the model to the observational data. So what's the problem? You know, how do we address this? You know, what could dark energy be? Well, you know, it could be some new particle or field that we haven't yet discovered. So this is referred to as dynamical dark energy. It could be that gravity itself is behaving in a strange way on the very largest scale. So just like Newtonian theory works very well if we're looking at weak gravitational fields, if you're looking at, you know, satellites moving around the Earth or the Earth moving around the sun, Newtonian theory works very well. But when you start going to very compact objects or very strong gravitational fields, then Newtonian theory fails, right? So it's a failure of the theory of gravity. Well, the same could be true of Einstein's theory when you look on the very, very largest scales in cosmology. So that could be the reason why the universe is accelerating, because it turns out that these modifications of general relativity naturally lead to an accelerating universe. It's one of the nice features of these modified theories. So it could be that gravity is behaving badly. And if that's true, then it means that general relativity is incorrect, at least on the very largest scales. And that would be a monumental result, you know, to show that at least at some limit, Einstein's very famous theory, which has worked so well over such a long time, over more than 100 years, is starting to fail on the largest cosmological scales. So that's quite an exciting prospect. So what about the future? Now, it turns out that the acceleration of the universe could potentially lead to what is referred to as the Big Rip. So if you kind of think about what's happening, the universe is accelerating at a faster and faster rate, and eventually that acceleration is going to rip the universe apart. And the nature of the so-called Big Rip depends on what dark energy is. So it's very closely related to the kind of dark energy models. And in fact, you can come up with dark energy models that lead to a Big Rip in like 5 or 6 billion years' time. So in a relatively short period of time, cosmologically, we hit a Big Rip. And then there are other cosmological models, like the standard lambda CDM universe, where you just have a constant dark energy, where the Big Rip will only happen far into the future of future evolution of the universe, and certainly not at a time to concern anyone. So it's very dependent on the kind of theory of dark energy. So it's something which certainly needs to be addressed. It could also be that, you know, one of the other features of modified gravity that seems to appear is that there are models of modified gravity which lead to cyclic universes. So you have then a universe that goes through kind of periods of expansion and recollapse, and then there's a rebirth, and then the universe goes through another cycle. So that could be another possible future of the universe. So there are lots of things that need to be investigated when looking at different theories of dark energy or modified gravity. Okay, so that's kind of the cosmology. So that's my day job. So I get to go to university and I get to play with very nice equations all day long and come up with crazy theories for dark energy. But then I get to go home and I can point telescopes at the night sky and take some very nice pictures. So this is kind of an interesting problem from the point of view of trying to do this from the city, because you all know you go outside at night and you look up and you kind of see this, right? So this is Cape Town, but Potchefstroom is much the same. It's a heavily light polluted city, and you might wonder, well, how is it even possible that you can go and take pictures of galaxies and nebulae, really high resolution pictures of galaxies and nebulae, given the fact there is all this light pollution? It seems like an impossible task. But it turns out that luckily technology in the design of filters and in cameras and in optics of telescopes have come so far, and for the most part, until relatively recently, it's been the domain of the professional astronomer. They've now kind of hit the sort of amateur community, and it's really possible now to use this technology and put together rather sophisticated instrumentation that you can run out of your backyard and take some amazing pictures, and in fact even do science with. So it's really quite amazing what these advances in technology, particularly camera technology, what impact that's had on the area of astrophotography. Back in 20 odd years ago, people would use a standard camera with film, okay, and they would try and take pictures of the night sky with film, and you wouldn't know what you got until you processed the film. Now you get instant gratification when you using a digital imaging camera in astronomy. Now this is kind of the sort of light pollution map of where I live. I live in Newlands in Cape Town, and it's pretty bad. If those of you who know, there's a scale, it's called the Bortle scale. So Bortle 1 is the night sky you would get at Sutherland, for example, or in the Cederberg, right? And virtually no light pollution at all. That's Bortle 1, and Bortle 9 would be the center of a big city like London, okay? And I'm kind of sitting at Bortle 7, okay? Pointing, luckily there's a mountain which blocks the center of Cape Town from where I live, so that's quite helpful. But I get a lot of light pollution from the south, so a lot of the light coming from the south will pollute my night sky. So it's Bortle 7, and that's pretty bad. You want to be imaging from at least a Bortle 3 or 4 zone. Bortle 7 is challenging, but there are worse places. So here's a guy. He actually runs a YouTube channel. He takes pictures from his balcony. He's able to take amazing pictures from the white zone. So Bortle 7 compared to him is really not that bad at all. So if he can do it, then certainly I can do it. So how do we get around the various challenges to take pictures? And essentially the main issue is to do with noise, right? And there are a bunch of different types of noise that you have to deal with. The first one is thermal noise. Now, anyone who's used a DSLR camera will know that if you take lots and lots of pictures, one after another, so you have short exposures, and you put your hand up against where the sensor is, well, you feel some heat, okay? So you feel the sensor heating up, and that's thermal noise, and of course thermal noise is going to mess up your image. So one way of tackling thermal noise with these modern astronomy cameras is to cool the sensor down. You can virtually eliminate thermal noise entirely. So these sensors can be cooled down in South Africa, so the ambient temperature at night is probably around 14, 15 degrees in Cape Town. You can drop the temperature down of the sensor to about -10. If you're living in North America in the middle of winter, where it can get down to minus 10 or -20 degrees in some places in Canada, then you can actually get your sensor down to -30, -40 degrees below ambient. But -10 is already cold enough to pretty much kill all your thermal noise. So that's already something. You've got rid of thermal noise. Then you've got something called read noise, which is basically the process that takes place in converting your photons into an electrical current, okay, which is what then is converted by your ADU into a signal that's read and converted into your image, right? So this is called read noise, and there's a lot of statistical uncertainty around read noise. And the fewer photons you have, the higher your read noise. So what you want to do there is you want to expose your camera for long enough in order to so-called swamp the read noise. Now, this is very easy to do in a city. So this is the only advantage you have taking images from the city, because you have so much light pollution, you are going to swamp your read noise within a second, even less, right? So read noise is certainly not an issue when it comes to taking pictures from the city. If you go out to Sutherland, you will have to expose for much longer in order to swamp the read noise. But that's typically 3 or 4 seconds or 5 seconds. It's again not going to be a big problem with these modern cameras. So then we have something called shot noise, and I guess this is the best way of explaining shot noise is that if you think of your sensor as being like a grid of, it's a grid of pixels, and you think of each pixel as being like a little cup collecting droplets of water. Now, if it's spitting, with rain, then these cups are going to sort of randomly collect water in a very random way, and you're going to end up with a very mottled kind of image coming out of that. Okay. If it pours down with rain, then your cups are going to fill up very quickly. Okay, and you're going to basically saturate your pixels and get get a much cleaner image. So you want to kind of be in between. You don't want to saturate your pixels too much, because then you end up with a white image if you saturate all your pixels. So you want to kind of have a balance between total saturation and the sort of just the little sort of gentle rain on your cups. So the way to do this is to, well, there are two ways of doing it. One is to take lots of subframes, okay, of a certain exposure, and add all those subframes together to give you a image with a much longer exposure. So instead of opening your shutter for 20 minutes, okay, you take 21-minute exposures, right? Or even shorter. It turns out, again, in a very light-polluted area, a 1-minute exposure is rather long. It's actually too long, because you're getting a lot of light pollution being captured by your camera. So the trick is actually to take lots of short exposures. Okay, we already know that with short exposures you can swamp the read noise. That isn't a problem. And you just take hundreds and hundreds and hundreds of short exposures, and in that way you build up your signal, which grows linearly, and your noise basically grows like the square root of the signal. Right? So very quickly, the more exposures you take, you're going to dominate your noise, and you're going to get a nice picture. So the way of getting around these sort of issues with light pollution and other forms of noise is essentially to take many, many short exposures. Okay, that's certainly one way. Another way then is to also add filters, which cuts out your light pollution, and I'll say more about that later. Okay, so that's shot noise and read noise and thermal noise. And light pollution. Then you've also got other kinds of noise, something that's called fixed pattern noise, and this typically are your hot pixels, right? So anyone who's looked at an image will sometimes see pixels which are, either black or white, and these are basically dead pixels or hot pixels, but they can be calibrated out. So what you can do is you can take calibration frames, and you can subtract the calibration frames from your so-called light frames that you've captured, and that removes the hot pixels. And then you get another kind of noise called walking noise, and that's due to the fact that sometimes you get these hot pixels, and because of you've got a low quality mount, or there's some drift in your image, and your hot pixel kind of drifts across throughout the night as you're taking frame after frame after frame. So you kind of get, when you then add all those frames together, you stack all those frames together, you get a streak. And that's kind of walking noise. And there's a very clever way of getting rid of that, and that is to basically move your telescope by a very small amount. And when I say a small amount, I mean by a few pixels, 2 or 3 pixels after each frame. And in that way, you kind of randomize that noise, and it all averages out. So you end up then with no artifacts appearing due to walking noise. So that's a process called dithering. And it works incredibly well. If you take an undithered image and compare it to a dithered image, you see a massive difference. Right, so these are kind of issues with noise. So now, well, what's the process of capturing images of space? Well, I've kind of broken it down into 10 not so easy steps, because each step, it's in itself is quite challenging. But essentially what we have here, well, first, you've got to start with equipment. You've got to put together some telescope and camera setup and mount. You've got to get something which is actually going to work for you. The next thing you need to do is you need to align your telescope. So your mount would typically be a German equatorial mount, so you can align it along the axis of rotation of the Earth. So what you do then is as the Earth is rotating, the telescope is rotating at exactly the rate in the opposite direction of the Earth, and in that way your image, your galaxy or your nebula is stationary, right? So that's the purpose of a tracking mount. But you have to polar align it. You have to align it along the axis of rotation of the Earth. Then you've got to plan your imaging session. That takes a fair bit of work. You've got to plan what target you're going to look at. You're going to have to plan, what the length of exposures you're going to take. You're going to have to plan, the timing of all of this, because the object will set and it will rise at some time and will set at another time. There might be obstacles like buildings or trees in the way. So you have to kind of manage all of that in your planning. Once you've done that, then it's all a question of framing up the target, setting the exposure and the gain, or ISO if you're familiar with DSLR cameras, and then off you go. And then, once you're going, you do something called guiding. I'll say more about that later. You launch your sequence, and then you let it run throughout the night. And in an ideal world, you don't want to stay up, because I've got to go to work the next day. So I've got to go and give a lecture at 8 o'clock in the morning the next day. I do not want to be staying up till 3 o'clock in the morning. So sleep is really important. So what you want to try and do is automate as much of this process as possible. And then once you're done, assuming you've managed to automate everything, is you get up in the morning and you can process your data, and then you get a final image. So it's quite a laborious task, and sometimes it'll take me 3 months to produce one image, because I'll get cloudy nights, I'll get nights where the weather's bad, and it'll take me a long time to collect enough data to produce a decent image. So, so back in at the start of this whole astrophotography adventure, I would be setting up every night on my deck at home in Newlands. And these telescopes and mounts they're pretty chunky things. They're very heavy. And doing this night after night, you're setting it up and then tearing it down in the morning is, at some point you kind of say enough. Can't do this anymore, especially if you're having to work the next day. So then the sort of compromise thing, the sort of next step was, okay, well, I'll just leave the mounts out. I'll cover them. So I'll leave the mounts out, and I'll just bring out the telescopes when I need to use them. Okay, so that was kind of the next step. But still, very time-consuming having to bring out the telescopes every night. So in 2020, during the sort of lockdown, or actually the second lockdown. It was, we've been through one period of lockdown and entering the second period. I thought, well, to hell with all this setting up and tearing down every night. I'm going to build an observatory. So I came up with a design which had to be cheap. You know, I didn't want to spend a fortune on another building. So I came up with a design where I built a what's called a roll-off roof observatory, and the materials were essentially the same as what you get when you put together a big freezer unit or refrigeration unit. So I used refrigeration paneling as my raw material. So this all happened in 2020. I had all the panels manufactured off-site, and then over 2 days, a small crew of about 5 people came and assembled the observatory on my deck, and then put a little sort of gate motor to motorize the roof, so I could open the roof with a little remote. And this was the birth of Silver Tree Observatory. So this is now what is sitting on my deck, and contains my telescopes. So all I have to do now is essentially, you know, open things up and start imaging. I don't have to set up. I don't have to do anything. I don't even have to polar align. Once I'm polar aligned, it's good for at least a year. I will check then after a year that the polar alignment is still good, but it's pretty reliable. I don't need to. I just lock everything down and it stays the way it is. So this is kind of the inside. These are a couple of the instruments that I have in there. These are refractors, and then the instrumentation I have in it at the moment are 2 different types of telescopes, which I'll say a little bit about in a moment. One's a Schmidt-Cassegrain, and the other one is kind of also a Schmidt-Cassegrain, except it has the prime focus at the front of the telescope rather than at the back. And this gives you some rather nice advantages when it comes to gathering light very quickly. And I'll say more about that in a bit. So this is a view from inside the observatory at night. So, you know, you can see stars. It's not that it's completely blocked out by light pollution. You can even see the Milky Way. So not very well, but you can see it. So I've got a little camera which is able to capture the night sky upwards from the inside the observatory. Okay, now that was kind of the setup for a while, where I had to press a button to open the roof. Okay, so that was already much easier than carrying everything out. But I didn't want to stop there. I wanted to fully automate everything, right? So I wanted to create a system which I could operate from anywhere in the world. I just log into the computers in the observatory, and I open everything up remotely, and I run everything remotely. Right? So I don't have to be physically there. So this relies on a bunch. So the first step behind this is setting things up in such a way that the computers in the observatory know what the state of all the different components are. So they know that the roof is open or closed, and this is done via magnetic sensors. This is the one sensor which indicates that the roof is closed. There's another pair of sensors which are activated when the roof is open. And then there are sensors on the different mounts, and they're important because they will tell the computer that whether the telescopes are low enough in order to close the roof safely, because the last thing you want to do is close the roof while your telescopes are pointing upwards, because they'll destroy the telescope. The roof will destroy the telescope. So you have basically a feedback mechanism where this little Arduino Uno controller reads the state of the observatory, of the mounts and the roof, feeds that into the computer software, the control software, and that then determines, you can then control, you can tell through software the roof to open, and also at the end of your night, you can program your software to close the roof automatically, right? Once the telescopes are parked in the correct position. So these sensors are really important. Without them, it would be rather risky running things, not knowing whether the roof could potentially close on your instruments. The other factor which is very important is weather. Cape Town weather can be a bit iffy sometimes. It'll start very nice during the night, clouds will then come over, and there's always a slight risk of rain. So I had to put up a little device here which measures the temperature of the sky, and that determines the cloud cover. And there's also a little rain sensor which determines whether it's dry or wet. Okay? And here's a sort of typical output that you get, a graph where here it's clear, and then it becomes cloudy, and then sort of clouds start to dissipate a little bit, but not really that much, and then it gets cloudy again, and so on, and then completely overcast over here. So you can monitor the weather at all times. So again, you have a feedback mechanism where the Arduino is also reading data from this little box, and if the weather, if it's cloudy, the roof won't even allow you to open the roof, right? So you've programmed your system to turn on at a certain time. You're in bed already, okay, fast asleep. It's programmed to turn on at, I don't know, at 12 o'clock at midnight. And suppose there are clouds it's overcast or it's raining. While this little device here will basically communicate with the computer via the Arduino to say, no, 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 you are not allowed to open the roof, right? So, so that's also a very, very important safety mechanism, because you don't want to get rain on your instrumentation. The other thing, of course, is you want to set up where once it's running, it's monitoring the sky the whole time. If the clouds come over, it'll send a signal to the computer to say, clouds have come over, there's a risk of rain, park the telescopes and close the roof. So if that happens, then the roof closes, or the mounts park, telescopes go to the park position, and the roof closes and everything shuts down. So this can all happen while I'm happily asleep. I don't need to worry about the possibility of rain or clouds while I'm fast asleep. And that's a great load off my shoulders, I have to say, but otherwise I would be fretting throughout the night, worrying about the weather. Okay, so just to give you a little demonstration. So this is done during the day, and it's kind of what happens. So first thing what would happen is you check that it's safe, and then the roof opens, and then once the roof is open, then the telescope will slew or move to its target. So there'll be a couple of seconds interval between the roof opening, and then you'll see the telescope starting to move. There we go. So then it'll slew slowly to the target, and then it'll begin the imaging session. And then at the end, it'll park the telescope and the roof will close. Right? So that's a sort of typical sequence of events that would take place. Okay. Now, of course, as I said, you need computers to manage everything. So each telescope is controlled by Intel NUC mini computer. And then there's a third computer which controls a little camera with a fisheye lens, and that allows me to take time-lapse pictures of the session during the night, which are kind of nice to do. And in fact, I think I've got an example of just that. So here's a time-lapse. So this is taking a picture roughly every 30 seconds and then creating a little movie. So of course the telescopes don't move this fast. The Earth is not rotating this fast, but this is a whole night session. And then once it's done, you'll see the telescopes will go to the park position and the roof will close. So there we go. Okay. So so this is over maybe 5 or 6 hours, sort of compressed down to 10 or 15 seconds. Okay, so what do I have in the observatory currently? So I've got kind of two different telescopes. One, which I've kind of called Big Bertha. It's the biggest telescope I have. This is mainly dedicated at looking at galaxies because it gives me a very close-up image. It gives me a lot of reach, and the field of view is quite small, so it allows me to image galaxies, and it also allows me to look at planets and the moon, which you want to get nice and close-up images of. Now, there are a bunch of devices I want to kind of sort of highlight here, just again related to the automation. So this is what's referred to as the imaging train. So here you have it's a focuser. So you can automate the focusing as well. So you don't have to physically go into the observatory to focus to get a focused image. This will happen automatically using a focuser, and the precision of the focuser is 0.04 microns. So it's highly precise. So you can get very precise focus with this robotic focuser. Then you've got a filter wheel over here, so you can change your filters throughout the night, depending on what you want to the light that you want to capture. Again, that can be fully automated. And then here's your camera. So all of these different components are all plugged into the computers and controlled with the control software and fully automated. So these are some examples of images taken with this telescope. This is a very famous galaxy, NGC 6744. It's a nice sort of almost face-on spiral. What you see here, which I always find very nice, is just this little fuzzy patch here is actually a satellite galaxy. And you can see one of the spiral arms is kind of swinging out here, and it's actually gravitationally interacting with this satellite galaxy. So this would be a little bit like the Large Magellanic Cloud, which sits just outside our galaxy, one of the satellite galaxies of the Milky Way. So this is NGC 6744. Then we've got the Sculptor galaxy, also very famous. And then we've got Centaurus A, with a sort of active galactic nucleus, another very famous galaxy. Very nice objects to capture with this long focal length telescope. And then going to sort of lunar and planetary imaging. So with a large focal length and therefore very high magnification, you can take close-up pictures of the moon. And the challenge you have there is, of course, you're shooting through the atmosphere, and at very long focal length of high magnification, all the little fluctuations in the atmosphere get magnified. And you can see this in real time. So this is a video taken of the moon, and you can see the sort of jiggly, the sort of wobbling here, like jelly, is due to the atmosphere. Okay, so it jiggles around like this. So you might, well, how do you get an image from this mess? Well, what you do is you capture video. Okay, so this is a video, and it's comes in at about 100 seconds worth of video, and about 1,700 frames. So the frame rate is about 80 frames a second, thereabouts. So what you do is you generate all of these frames, and then the software will select the best frames, because in between all this jiggling, you will get these little glimpses of clarity, right? The atmosphere will be still, and those are the frames that you want to capture, right? So the software will identify the best frames, and then you stack those best frames, and then you end up with something that looks like this, right? A much cleaner image of the moon, okay? And you can do the same thing with planets. So here's an example of Saturn. Again, you take video, you take many thousands of frames, you select the best frames, and you stack those frames to get an image. Now, Cape Town is not the best place for planetary imaging because you're close to the sea. There's a mountain as well, and that's not great for distortion of the atmosphere. Gauteng, on the other hand, is great. You know, if you go, and probably in winter here, planetary imaging is also pretty good. So it's not something I do very often, but it's great fun because, you know, particularly if you're doing outreach, you have sort of live images, you know, video from the outer planets, which you can project and show school kids. Okay, so the other telescope in the observatory currently is what I call Speedy Gonzales. Now this is kind of on the other end of the spectrum when it comes to the field of view and also the speed. When I say speed, that's the ability to capture light. And it's roughly 20 times faster than the other telescope. So it collects light about 20 times faster than the long focal length telescope. And this is a telescope which is kind of modeled on sort of the Schmidt astrograph type setup where the prime focus sits over here rather than at the back of the telescope. So this is the Anglo-Australian telescope. It's got a mirror size of 3.9 meters. So mine has only got a diameter of 0.2 meters, so it's much, much smaller. But the operating principle of the telescope is exactly the same. The prime focus sits here rather than at the back. So here you can see where the camera is sitting over here. It's not sitting at the back. So this is where the light comes to focus. So this is great for taking wide field images of nebulae. So typically you're looking at objects which are several moons across. So if you look at the size of the full moon, so the Rosette Nebula would be 4 or 5 full moons across. Okay, so very big objects. Not easy to see with your naked eye, but you need something with a wide field in order to capture it photographically. So this is the Rosette Nebula. Here's an image of the Eta Carina Nebula. That you can, of course, see with your naked eye. Not in color like this, but you can see it in the Milky Way in the summer. It's rising now in the early morning. And this is, of course, the famous Orion Nebula, also visible now sort of after about 11 o'clock at night. So these are all big nebulae, so wide field objects. And then just a fun comparison. So, of course, this is taken with my, relatively cheap, certainly not, $4.7 billion, but relatively cheap RASA of the Pillars of Creation in the Eagle Nebula. This is taken with a Hubble Space Telescope. And this is actually not too bad, I didn't have to spend $4.7 billion to capture that image, right? Okay, then I've got other telescopes, different types. These are refractors. These are also wide field, but they're a little bit slower than the Schmidt astrograph, but they are easier to manage. The very fast Schmidt astrograph model, that's great, but you've got to bear in mind that the critical focus zone on those telescopes is typically around 8 microns. It's nothing, right? So the image plane, your camera, your sensor has to be perfectly aligned to within 8 microns in order to get a nice flat image without any artifacts on the edge. If you use a refractor, on the other hand, then it's much more forgiving. You don't tend to have these issues on the edges that you get when using large sensors with these Schmidt astrographs. So it's a balancing act. You've got to kind of decide whether you want really the ability to capture light really, really fast, and then you deal with these artifacts, you crop your image to remove them, or you sort of go with something which is going to be a little bit easier to manage. The field of view, incidentally, of this telescope is exactly the same as the RASA, as the Schmidt astrograph. So this is a picture taken of the Fighting Dragons of Ara, NGC 6188. And this is part of the Vela supernova remnant. This is called Pencil Nebula, because it kind of looks like a pencil. And this is the Tarantula Nebula in the Large Magellanic Cloud. So these are, again, these are big wide field objects. But with a refractor, because it's f4.4 as opposed to f2, it's slower. It'll take longer to collect the light than with the faster instrument. So will take longer to capture these images, but you don't have to worry so much about there being artifacts around the edges, and you don't need to worry about really precisely collimating your instrument. So it's swings and roundabouts what you really want to get out of this. Okay, now of course you want to go to dark sky areas. You want to go to the Cedarburg or to Sutherland, places where it's really dark. And that means packing up all your gear, putting it into the back of your car and driving off. And if you've got a family, got kids, it's not practical, right? Basically, this is the entire boot and the passenger seats taken up with equipment. So you end up taking 2 cars up to the Cedarburg instead of 1, and that's too expensive. You know, petrol is just too expensive to do that. So you need to find something which is going to be easily portable. So I lost the battle, with taking the heavy gear up, and I ended up investing in a smaller instrument. So this is very wide field. So this is able to capture the entire Large Magellanic Cloud in one frame. And it's essentially just a lens. It's a 135 millimeter lens. It's pretty fast, f2.8. And you basically put a camera on the back of it, and off you go. And it sits on a very lightweight tracking mount, very easily portable, and great to take away to dark sky sites. Okay, just to give you an idea of the different fields of view. So the inside box here is the very long focal length telescope, so that you just about get a full moon, a little bit less than a full moon in. With that telescope. Then the next box is the Schmidt astrograph or the refractor. They have the same field of view, so that's quite a lot bigger. And then this big box out here is that 135 millimeter lens. So that's very wide. Okay, so that's great for capturing things like the Large Magellanic Cloud or multiple objects in a single frame. Okay, so let me talk about some of the sort of key steps and tools in the sort of general workflow that has to take place. I have already mentioned polar alignment. So the issue here is you want your telescopes to be aligned along the axis going through the center of the Earth. So this is towards the south celestial pole, and the mounts rotate opposite the rotation of the Earth to counter the rotation of the Earth around that axis. And you have to get that really tuned in very precisely to get good tracking. Now nowadays, you don't, in the old days, you kind of crawl down and look through a polar scope and do it kind of manually. Nowadays, we do it with software. So basically what you do is you point your telescope, you take a picture, the software will basically tell you how far you are away from the south celestial pole, and then you basically turn your knobs in your mount iteratively until you dial in to very precise polar alignment, okay, and really precise. You can get it down to, fractions of an arc minute. And anything less than an arc minute is very good, but you can actually get it down to much less than that. So that's polar alignment. Then, as I mentioned, the idea of guiding. So guiding is very important when it comes to imperfections in your mount, because normally you wouldn't be able to afford the sort of observatory class mounts, which are able to track very, very precisely. They cost hundreds of thousands of rand. That's just not feasible. So you buy mechanically sort of inferior mounts, but because of that mechanical inferiority, the gears aren't kind of meshed perfectly. You end up with imperfections, but you can correct for that through the process of guiding. So you follow a reference star, and the software measures the deviation away from that reference star from your fixed point, and then it sends a signal to your mount to push the mount back to that point if you're deviating away from it. And it does this, every second or every half a second throughout your session, and you can get precision, guiding RMS down to less than half a second of arc on the sky. That's the angle on the sky, and that corresponds to 0.0002 of the diameter of the moon. Or in terms of your sensor, it corresponds to a fraction of the size of a pixel on the sensor. So if you're at the fraction of a pixel, then any kind of movement you're never going to see that movement, because it's at the scale of less than a pixel on your on your camera sensor. So guiding software has really been revolutionary for amateur astrophotography. It has been a complete game changer for the field. The other really important issue is, yes, particularly in light polluted areas like Cape Town or Potch, is our filters. So you want to have filters which are able to cut out the light coming from street lamps. Okay, sodium lamps, for example, and you want to cut that light out. So you can design filters that basically will cut out. So here it's cutting out the ultraviolet. Okay, over here. Here it's cutting out the sodium coming from sodium emission from your sort of street lamps. Here it's cutting out the mercury lines. Okay, so this is cutting that out, and what you're left with is essentially what you want. You're left with blue and green, red, and then over on the far infrared, it's cutting out the far infrared light as well. So basically, you're just extracting the visible parts of the spectrum, and you're cutting out all the unwanted light pollution, or at least not all of it, but a fair fraction of the light pollution you're cutting out using this filter. So that is for imaging in true color, in red, green, and blue. Then there are other filters that you can use, which are very specific to particular wavelengths of light. So in emission nebulae, you're going to get a lot of light coming from hydrogen emission. You know, when your electrons are sort of bumped up to high energy levels and they drop down and they emit light in that sort of quantum process. You're going to get light at certain frequencies, and the usual frequencies, the typical frequencies are around 500 nanometers for hydrogen alpha, and then, for oxygen 3, and then 600 nanometers for hydrogen alpha, and then the other one is sulfur 2, which is just at around 650 nanometers. So you can basically cut everything else out and just look at those particular frequencies of light. And that's great in a light polluted area. Then what you do is you use different filters for the different wavelengths, and then you map those images, map that data to red, green, and blue in any way you want. So basically, typically you would map hydrogen to red, okay, but it's typically in the red end of the red part of the spectrum. You'd map oxygen to blue and green, and sulfur, you kind of also map to, you sort of combine hydrogen and sulfur to the red channel. Or you can take any combination you like, right? So it basically becomes an artistic kind of thing, how you want your image to look. So you can get very artistic about how you map these different channels to the color channels in your software to get a color image. Okay, so actually, before going on to this, so let me actually show you a couple of things related to that. So here we've got, so let's start with a color image. So here we've got, this is now your blue filter. So this is the Pleiades cluster using a blue filter. So you capture your blue light. Now you use a red filter. This is your red light. You can see it looks very different. It's much brighter in blue than it is in red. And then here's your green, okay? And then you combine those channels together to get a color image. And here's your color image, right? So RGB, red, green, blue. So you take your individual filters, you capture red, green, and blue lights, and you combine them to get a color image. So that's a true color picture. Then the other thing you can do is you can go to narrowband. So now let's look at a narrowband type situation. So here is an image of the Tarantula Nebula. So this is the hydrogen emission. Okay, so this is hydrogen, very bright in hydrogen. Then this is your oxygen, okay, also quite bright. Oops. So this is oxygen. and then this is sulfur, right? So those are your 3 narrowband filters. Sulfur looks very different to oxygen and hydrogen, not that strong. And then what you do is you map those to a false color image. So you go and take those and map it any way you like. So typically there are different palettes that you can take. So here is one palette where you map H to hydrogen to red, oxygen to green, and oxygen to blue, right? It's called HOO. So that gives you, oops, actually let me run it. So this is now taking that palette, combining those images. So this is a image that it's not true color, it's false color. Okay, this is a false color image. But it tells you important information, scientific information. It tells you the red areas, this is where the hydrogen emission is, and the sort of bluish greenish area is where the oxygen emission is, right? Then you can also do what's called the Hubble palette, made famous by the Hubble Space Telescope. And there what you do is map sulfur to red, hydrogen to green, and oxygen to blue. Right, so you do that, you get a completely different looking palette. And it looks something like this. Okay, so again, you can see the green here is where the hydrogen is, and the blue is where the oxygen is largely located. So scientifically, you can get a lot of information from these false color images, but they're not real color. You're basically taking those particular wavelengths and mapping them to the color channels to get a false color image. Right. Okay, so, and you can, the thing is, you know, there are an infinite number of ways you can do these combinations. So people go crazy. You know, they actually can construct mathematical formulae for the different channels, which will combine all these different wavelengths in a rather complicated way to get exactly the kind of picture that they're looking for. You can even basically create images that look like true color by combining the narrowband data in a particular way. So there's a lot of fun you can have combining these different data sets. Okay, so this is all fun, you know, doing astrophotography. It's great fun producing these images, but it's not really the only reason I'm doing it. There's another reason, and it's a powerful way of bringing astronomy and bringing science to the community, to particularly school kids. Because if you think about it, astrophotography involves so many different elements. You've got photography, you've got computer science, you've got automation, you've got robotics, you've got astronomy, you've got data processing. All of these different things sort of blended together are needed to produce these images. So you can teach a lot to young people about all of these different things when talking about astrophotography. So what I do is I run these open nights. So this here is actually going to a school in Parklands in Cape Town and actually doing a live imaging session. So logging into my observatory remotely from the school. It was during the winter months, so it got dark early, so I could do it. And actually capture images in real time and demonstrate the entire kind of workflow and the entire process that I need to follow in order to capture these images. So this was Parklands, and these two images here are taken in the Cederberg, at the Cederberg Astronomical Observatories, where we have open nights every Saturday. So I'm part of a group of 6 people. We have a rota, we go up every Saturday and we run these open nights. And they're generally very well attended. You know, during the school holidays, we can have up to 100 people attending these open nights. And we're combined with me now on the team. We're combining both visual astronomy, where you actually look through eyepiece of telescopes, and also the astrophotography side as well. And we can do a direct comparison of what you see with your eyes with what you see with a camera. So that is the sort of outreach component or outreach aspect of this activity, which I think is really probably the most important part of why I do this, is really communicating the joys of astronomy and astrophotography to young people. Okay, so if you are interested in this kind of thing, feel free to contact me, and you can also find me on social media under Astro Cape Town, have a look at the kind of stuff I do, and if you are interested to learn more, feel free to contact me. I know we're kind of running out of time. What I want to do very quickly, just to show you that I'm not just talking nonsense when I say you can kind of remotely control, you can sort of remote into the observatory. I'm going to do exactly that over here. So I'm going to now connect directly to one of the main computers in the observatory. So here we have, this is now the NUC, which is controlling the weather station and the roof, and also monitors the humidity and temperature of the air around the telescope. And what you can do, you see here these toggles here, I can turn the power on and off. So remotely I can go and turn the power of the telescope and the instruments on, and I can turn it off, right, remotely from Potchefstroom. So this is in Cape Town, and I'm doing it from Potchefstroom. I can also go and there we go. So this is now looking down on the observatory there's a camera on my roof looking down. And this is again live from Cape Town. So you can see the time here. It's 20 past 7. So this is real time. And if I wanted to, I could open the roof remotely. Now I can't do that because if I go over here, in fact, if I just drop down first over here and look at the weather, you see that the state which is being indicated here is red, which means it's not safe. If I look at the graph over here you can see it's cloudy. It's currently cloudy, right? So it's unsafe. And if I now go to the control software, and I go to the equipment, and I look now at the safety monitor, you can see here there's a little red dot that's indicating it's unsafe. And if I go down to the dome, if I were to try and open the roof, then it would prevent me from doing so because it's not in a safe state, right? So I can't open the roof because it's not deemed to be safe. Of course, I could go, if I were on site and I had my regular remote, I could override this by simply pressing the button, but then I'm on site and I can look up and I can just check that it's not raining. But I would never want to try and open the roof from Potchefstroom, okay, because if the weather's poor, it's potentially a risk to my equipment. So this is the safety monitoring of the equipment. So you can remote into these computers. That's one of them. Let me just show you just another one. So if I go into this computer, this is giving me a live stream from inside the observatory. So you'll get, so this is now live from inside. There's a camera which is sitting in the corner, and these are the two telescopes. So I can monitor what's happening inside. And when the roof is open, this camera also then allows me to take time-lapse pictures of the night sky throughout the night, which is a kind of fun thing to do. Okay, so I think I'll end it at this point, and thanks very much for coming through and bearing with me. I know I'm running a little bit late, and if you have any questions, please go ahead.
Thanks, Peter. It was very interesting, quite a rich experience if you summarize all those 10 steps and so. Dark matter, dark energy, or astrophotography. There's one, yes? With cyclic model.
It's really, this telescope is going to be able to, just to give you an example, which I'm particularly excited about because it's something I'm dabbling in even with, with one of my telescopes here, is the search for, looking at exoplanets, looking at planets around other stars. So you can, with my larger instrument, you can actually measure the light drop due to the fact that you've got a large planet moving in front of the star. So this works for sort of Jupiter-sized planets. What the James Webb Telescope is going to be able to do is going to be able to look at rocky planets, right? And not just, at a small sample of stars, it'll be able to capture exoplanets for potentially thousands of objects, and also analyze the spectrum, from the atmosphere, so determine the composition of the atmosphere around these planets. So from the point of view of searching for life, for the conditions for life, James Webb is going to make huge strides in that direction. So that's just one example. So yeah, it's a game changer. I just hope that there aren't any major technical issues that will come up over the next years as it operates. There's already been one issue with one of them, dust flying through space. There are obviously risks to the experiment, but let's hope that it's able to run for many years and collect lots of amazing data.
In one of your photos inside the observatory, you had labeled a lot of things, but one of them was not labeled, and to me it looked like a dehumidifier.
Yes.
Do you run this constantly when you take photos?
Yeah. No, not when I'm taking photos. So only during the day, and in winter, it's critical, right? Because Cape Town winters are very damp, and the humidity is very high, and it'll collect several liters of water a day.
Is it automatically taken out as well?
It's automatic. It comes on and off automatically. Yeah.
Okay.
Yeah. Yeah.
1, 2, good. So you had pictures of 2 photographs of, I think it was a nebulae, of a
Yeah.
nebula, rather. So the other one you say is from a Hubble telescope, I think, and then you said it cost something like 13 billion.
Yeah, $4.7 billion at the time. And Hubble,
Woo.
when did Hubble fly? It was, yeah. So that's money from like several decades ago, right?
Yeah.
So very expensive.
Yeah, but you didn't put the price on the other one. How
Oh, I
much?
didn't
How
put the
much
price
is
on
your
the other.
equipment? That's what I'm asking.
Oh, right. Okay. So that particular telescope comes in at about $1,500, a bit less than that, $1,200.
Really?
So a lot less than 4.7 billion. No. I'm getting quite interested in cyclic universes, and I'm also getting quite interested in decaying dark energy models. So this is a kind of dynamical dark energy model where the dark energy decays over time, which means that eventually cold dark matter will dominate again. And if the universe is even slightly positively curved, slightly closed, then that would mean that the universe would recollapse in the future. So that's a really, if we discover that dark energy is decaying, that it may end up that in the far future, the end state of the universe is in fact a big crunch. Or maybe the beginning of a new cycle, because if the conditions are right, during the recollapse, maybe you get a bounce and then the universe starts again. Right? So decaying dark energy models are kind of quite interesting. Yeah.
Let's see, Amar, do you have a few words you want to say, or should we just conclude?
I just want to
Thanks. Hello? Yeah. Peter, thanks so much for the interesting public talk and the interesting colloquium you gave earlier. And I hope this will be one of many future visits by Peter. Yeah, I just also want to thank you and the people involved in organizing this event. And also want to acknowledge funding from the Center of Excellence for Mathematical and Statistical Sciences for making this possible. Thanks.
Thanks a lot, everybody. Thanks for attending. And welcome to chat to Peter as well. He's still around for a few hours or day, half a day maybe. I don't know when you leave, but...
I'm here till, I don't know, what time do I leave tomorrow? Late morning. Yeah.
Late morning, so you can, if you want early breakfast, you can chat about dark energy, dark matter, and sunny side up eggs, maybe. Thanks, everybody. Enjoy your evening.